Yep.
representing.
Yep. If you go down to the bottom, I think it magically appears.
Nope.
Oh.
Yeah. Otherwise, I can send it to you, and you can send it to chat.
Yeah, that's right. I'm still sort of Slack challenged in some ways. If you email it to me or Slack it to me.
I Slacked it to you.
Okay.
Oh.
Okay.
So if you click on this link, then you can join the Slack channel for, I hope it's GLM. Yeah, it should be GLM. And there we have a channel for compilation issues, getting started channel for like all the questions we have, an ICE channel, and also a random channel.
It doesn't get a ton of traffic, I've noticed, but periodically it does. I've noticed that some of these things are really density dependent. If it's a Slack channel people use a lot, it becomes a huge resource. And everyone goes there. And if it's used infrequently, it's almost like it's like putting a message out into the emptiness, and you hope that someone pings back.
Yeah, I totally agree. We also have a Google, also GLM as a Google group, like a Google forum, which is also not that active anymore. But I mean, the more people join, the higher chance will be that it can become more active, I hope. But I guess community building is always a different, tough topic. How to engage people and.
Yeah. By the way, during today's workshop, we're hoping it's, at least somewhat interactive. We recognize that some folks are going to have challenges playing along just because of difficulties in installing and running the latest of the software. I don't think there's any way for me to see everybody's faces while we're in presenter mode. I think that's true, right, Kaylin? Right. So I can't see if you're sort of raising your hand or, if you've got a question. I think, we're a relatively small group. I'd say just pipe up or type it into the chat. And during the part of the workshop that Robert's running, which quite frankly is most of the workshop, I'll be monitoring the chat and also trying to keep my eyes on people to see if we can raise those questions.
Maybe it's just a preamble before we get started, right? At 10:30, because I think most of our crew is here. I think the only person who hasn't yet joined is Francois, but I think he knows he's got the link. To first thank you, Paul and Robert, for agreeing to do this today. So a lot of, when we were trying to solicit ideas for activities to be held at this virtual workshop in lieu of having in-person time together, having a GLM tutorial immediately emerged as something that would be of interest to a lot of our group, particularly because there's a lot of students that are working on GLM or GLM related questions for dissertation chapters. I think as I look around kind of the Zoom windows, I think if everyone could raise your hand who's directly doing GLM things, it might be helpful. You can kind of see, like, yeah.
You mean at this moment running it, or within the past day or week?
It is time scale dependent. Yep.
Yes. So this is really awesome. So to thank you both again, and also to leverage some of the tools that I know that you've been working on and shared at the GLEON meeting. But I think now it's like specifically more relevant for folks that have moved a little bit further in their projects. And then the second thing was also to introduce Robert. And so Paul, I'm wondering if I could turn over everything to you now.
Yep. So thanks, Kaylin, and thanks everybody for joining us today. My pleasure to introduce Robert. I think a lot of you have either met Robert or maybe interacted with him over email. Robert is a postdoc funded by the award that you see up there, the NSF ABI Biological Infrastructure Award, which is funded to help make GLM more accessible and also to upgrade some of the capacity of GLM and to do things like run this workshop. So a huge thank you, first of all, to Robert, who has done the bulk of the work in putting together this workshop and who's actually going to be the person running most of the workshop. We've got a number of different phases that we're going through in the workshop. Yep, up on the screen. Perfect. So hopefully some of you have had a chance to try the before the workshop activity, downloading the software, setting it up and trying to run it. We found out, I think it was yesterday or the day before, that Matt had released an updated version of GLM, which is really cool. The only downside is that the output of the new version of GLM will give you a different answer than the version of GLM we put together for the workshop. This is
what version did you use for the workshop?
Robert?
310A1. So not B, but A.
Wow.
Yeah.
And suddenly, at least for AED, things changed drastically. I don't know why. I looked at the comments and it shouldn't happen, but all my phytos died off.
Mm-hmm.
It happens sometimes.
Right. Water clarity's gone way up with the new version of GLM. We've improved water quality with just a modeling version change. So that's kind of cool. You know, just as sort of an interesting aside, for those of you who are new to modeling, this may be sort of shocking to you, which is we have a version change of the model, and now all of a sudden all of your answers change, you know, which makes you wonder what's really going on behind the scenes in the model. And one of the things that you sort of learn over the years is that, you know, the model is just a model, and there are a lot of assumptions that are built into it, and the configuration of the model matters, and versions of the model matter. And, you know, it's one representation of reality. And, you know, you've got to use your training and your scientific knowledge to evaluate what's working and what isn't working for you. GLM and GLM AED especially is a really wide topical area. And so when Robert and I were talking about, you know, how are we going to cover all this material in about an hour and a half? First of all, we decided we simply can't cover all the material in an hour and a half. And so we prioritized those topics that sort of were the intersection between what you all identified on the online spreadsheet. Thank you very much. The topics that were of interest and areas where we kind of felt like we had particular expertise, or in some cases, we had materials that were already prepared, so it could be efficient at putting together the workshop. So there's a lot more here than what we'll be able to get to, which means, testing your installation. All right. Oh, there we go. Thanks. So there's a lot more to GLM AED than we can possibly get to today. Don't hesitate to bring up any questions. We can always kick those cans down the road and answer them offline if we need to. For today, Robert's going to provide a series of slides as an introduction to GLM to give a little bit of the theoretical background, kind of get us warmed up with the concept of modeling lake physics. We'll jump into R and look at examples that show how to run GLM within the R environment to visualize the results, and then I'll work on something that Robert spent quite a bit of time on, which is calibrating GLM. We'll then step into an introduction of AED, biogeochemistry. It's a very big topical area. And so we'll focus on two specific topics there, dissolved oxygen and lake carbon cycling, and look at a couple of examples there. And then at the very end, if we have time, and we'll see whether we even get through all of these topics, depending upon your questions and how things run smoothly. But at the very end, we'll have time for a little bit of discussion, hopefully. But it's perfectly fine to have the discussion as we go along through the workshop today. So thank you all, and thanks again, Robert, for getting us prepped and ready to go for here. And I'm going to turn it over to you.
Okay, thank you. Good morning, everybody. And yeah, thank you also for inviting me. So before the workshop, I guess everybody did that. So installed GLM 3R and GLM tools. And then there are some more packages. I hope this all worked for everybody.
No, it didn't, unfortunately, but I don't know. I get this weird thing, incomplete.r profile. I restarted my computer, everything, but I don't know what it is. So
Oh yeah, I saw your email. Did you try installing the branch
the what?
with the WAV GLM version 3.1? I guess you're using a Mac system, or
Yes.
you could try maybe if you do this with the WAV command from GitHub, you would install a different branch. Maybe this one could work. Otherwise, I guess your .r profile error could be something beyond the GLM tools, something in the R installation.
Yeah. And Francois, I don't know when you connected, but I think it's the case we're going to really be challenged to solve kind of individual installation issues, which is too bad.
I know.
Today.
But anyway, so
Yeah.
maybe I won't be able to follow. That's okay.
But you can sort of play along anyway, I think. And we're happy to connect with you individually after the workshop and try to get things running for you.
Yeah, and also your error message is really interesting. That's a great error, but I have no idea how to solve it.
It's a new one, Francois.
It's
Francois, you just got complimented on your error message.
Yeah.
at last clear we had all different errors, but this one is new.
And Francois, you do so many more things well than this particular error message, so we won't let that define you.
That's very helpful indeed.
Yeah.
Okay,
I hope you can figure this out, but I think if it is related to your R profile, this could be something in the R installation itself. Okay. If you could install GLM tools and GLM3R, then hopefully you also did the first example, which was the automatic calibration of the hydrodynamics. And if not, that's also okay, because we will also run through it in 20 minutes, hopefully. So first, I want to give like a short introduction to GLM. So how it works, what is the theory behind it, what is the vertical 1D model, what is the mass balance, and how is mixing working. And at the end also gives a brief overview of some example applications. So the first thing, GLM, or the General Lake Model, started as a GLM project. So this is a global lake ecological observatory network, and was developed by Matt Hipsey, Lewis Bruce, and Caspar Boone at the University of Western Australia. And the cool thing about GLM is that it was designed to operate with a water quality model, which is the AED model, the Aquatic Ecosystem Ecodynamics Model Libraries. So if you want GLM, it's internally already coupled with water quality or an ecosystem model, which is really powerful. GLM itself is written in C, and AED is written in Fortran. So if you want to add new water quality modules to AED, you have to write some Fortran code, which can be a challenge because it's hard to learn nowadays, at least.
You also need to realize that C and Fortran index starting at 0 or 1, and it differs between the two languages.
So there's lots of fun if you want to do that.
Yep, details matter a lot. Yep.
It's freely available as an open source program, so you can just go to GitHub and download the code, compile it, and also change the code.
I think it's probably good for us to point out too that the USGS, Jordan Reed's group, put a lot of time initially into wrapping GLM in the R environment. And even though they're maybe a little bit less involved these days, a lot of that initial effort and credit goes to them.
Yes, thank you. So people are using different multi-dimensional models for lakes. So this is just like a brief introduction. So on the left side, some people, or most people, are using, for reservoirs at least, longitudinal, vertical, two-dimensional models, where you only look at the depth axis and one horizontal axis. Then in the center, you can see, I hope you can see my mouse.
Yes.
So you can see for shallow lakes, you can use a depth average two-dimensional model. So we just have two horizontal dimensions. On top right, if you're really going into all the hydrodynamics, you can use also a three-dimensional model. So you look at all three dimensions. And also lots of people are also using zero-dimensional models, so-called box models, where everything is completely mixed. A good example for this is a PC Lake, which is really popular in Europe. But GLM is a vertical one-dimensional model. So here you can see a really great schematic of how GLM operates. So you have all the inflows coming in. You have inflow entrainment, surface mixing, bottom mixing. Everything is over one vertical axis. Then you have all the meteorological drivers. You have snowfall, global radiation, you have turbulent heat fluxes, you have wind coming in, and then you have all the convection of heat to or through the water column. And you also have the outflow dynamics. So you have overflow, and also if you have a reservoir or like a really well-managed lake, you also can set the outflow dynamics of the GLM model to really replicate your management system, management plan. So GLM is really powerful and was used for a lot of different lake setups with different hypsographies and different management aims. So what is a vertical 1D model? So GLM resolves several layers over the vertical axis. And strictly speaking, if you use GLM, it's really only valid for stratified lakes where you assume that your vertical density structure is the dominant one and that your horizontal density structure is more or less homogeneous. So if you look at your lake and this would be your density profile, it would be the same at every point in the lake. So the vertical change would be the dominant one. And also, strictly speaking, if you use a 1D model, it's also more or less only really valid for lakes of a small to moderate size, where you have no effect from the Coriolis force or earth rotation on the lake flow dynamics. But you can still use GLM and get pretty good results, even if you have a large lake.
What, Robert? What do you think of as large?
Oh, that's a good question.
Yeah.
I mean, you can calculate when the Coriolis force will have an effect of a lake size. So, for example, Lake Mendota has a Coriolis force impact.
Okay,
So
and that's about 10 Ks across. Yep.
Strictly speaking, you can't use GLM.
Shoot! Already published that one.
But
Okay.
you can, it's still like, I mean, the pros for GLM or for most 1D models, of course, it's really fast. So you have low computational needs, and it's really great for investigating long-term stratification dynamics.
Yeah.
For example, a 2D model can use, if you want to simulate 1 year, it can use up to 1 to 3 days. And for GLM, you can do 4 decades in 2 minutes. And you can't beat that. So how does GLM work? So GLM, as you can see here on the right side, resolves several layers over the depth, and each layer is here a control volume, which can adapt its thickness over the course of a simulation due to flows, mixing, and mass fluxes. And here GLM is using like a setup of different thicknesses per layer, which we call a flexible structure or lagrangian structure. And the interesting thing here for this approach is that each layer has a unique density compared to its neighbors. And when there is enough energy, then you can overcome this density gradient, then layers merge, or also layers can split up. And here every layer also responds to a specific area at this depth, so also to a specific volume, which means a 1D model is not one point in the lake over the depth, but it's the whole lake system idealized as a one-dimensional approximation, because the whole volume of this thing is in this layer. So the whole water volume is like, yeah, I think you get what I mean. The mass balance of GLM is relatively simple. So if you look at the change of the volume over time, so the net water flux, it's just what happens or how much the surface layer height over time is changed, plus a sum of all the inflows and the outflow. So the inflow, the outflow, seepage, and an overflow. And everything is here and just solved by integration over time.
And Robert, does that also include direct precipitation and evaporation from the surface?
Great question, because this is in the second term here.
Oh.
So the second mass flux is for the surface layer height. So this one is calculated first in the code, and then all the other inflow fluxes are calculated. So if we look at the mass balance of the surface layer, so the change of the height of the water level over time, it's the sum of precipitation, snowfall, runoff of the riparian areas, evaporation, and ice dynamics. And also at the end, the inflows are also affecting changes in the surface layer height. The main thing is for GLM that mixing only affects the thickness of the surface mixed layer, but not the height of the water table. So mixing won't increase your water table, it will just deepen or deepen surface mixed layer thickness, or it will make it more shallow. So just the upper layer. So,
And what's the time resolution over which it calculates all the mixing?
normally the integration time is like 1 hour.
Okay.
You would use.
Mm-hmm.
So the main
There's
thing
a
for the
question from Xiaomei. I'm wondering if
yeah.
Xiaomei was wondering, is the flexible Lagrangian structure superior than Eulerian structure, or is it just easier to simulate?
It's more elegant. My experience having Eulerian structure is more stable mostly, because you can also then have like a shallow or more a more fine resolution grid on areas of the thermocline and at the surface, and then have like coarse grid at the bottom. So Eulerian structures tend to be more stable, but a Lagrangian structure has, at least according to literature, advantages in simulating the thermocline mixing.
So you mean the flexible structure is better at simulating the surface mixed layer?
I won't say that. I think both have advantages.
Yeah.
There are not that many models using a Lagrangian structure for 1D models.
Yeah.
Most use the Euler approach. It looks more elegant if you look at the results, and it's at least Matt Hipsey is saying in his paper from this year that it has advantages in resolving the thermocline layer, so it's more stable there if there's a lot of mixing happening. Because this can change over time, where in an Eulerian structure, you would have to resolve your thermocline thickness layers before the simulation starts, and here it's done dynamically over time.
Yeah, yeah, it's reasonable. Yeah, thank you very much for your answer.
But this is a really good question, and yeah, it depends what. I mean, I personally think the Eulerian approach is easier and more pretty straightforward to use.
Since I saw from the Diatom paper that the Lagrangian layer is somehow easier to simulate the tracer.
Like tracer dynamics, or
yeah.
maybe, I don't know. I mean, most like other 1D models like Gotham and SimSquared are using an Euler approach, and they also have really good results nowadays, or they really have really good results, especially for turbulence modeling with K epsilon. So it's a hard question. I don't know which one is superior.
There's also weighing the how well it integrates with data assimilation. That could tip a balance on a decision making. My gut is that a Eulerian approach would be more would better interface with kind of a fixed grid in a data assimilation framework than a Lagrangian. But we're working with the Lagrangian nature of GLM, and there's some things we do to kind of preserve the flexible structure of the Lagrangian format in data assimilation.
Yeah, I think yeah, it's hard to say which one is superior.
Yeah. Okay. For the surface energy balance, it's also the one used in most lake models. So the change from temperature over time times the density, the specific heat capacity, and the thickness of the surface layer. And this is the incoming solar radiation, the incoming long wave radiation, the outgoing long wave radiation, and two turbulent heat fluxes. One is the latent heat flux, so evaporation, and one is the sensible heat flux, which is then convection or conduction. So these things go all in to heat up your surface layer. And this is also one of the, next to the Lagrangian approach, one of the interesting things for GLM, because it uses for the surface layer mixing dynamics an energy balance approach, which means energy balance of the surface layer determines the thickness of the surface mixed layer. And below that layer, we have the Limnology or the thermocline, and below that, GLM uses a turbulent diffusion approach. So you have like a turbulent diffusion coefficient between two layers, which then governs how fast mixing processes happen. but in the surface mix layer, it's only an energy balance approach. And this means that here mixing depends on a difference between the potential energy of the water column in this layer and the available external kinetic energy. And here, kinetic energy is the sum of convective overturn due to cooling, wind steering due to wind, and shear production. And I have this really nice figure from Matt's recent paper. So GLM calculates all these different energy terms step by step. So let's start at the left side. So we have our initial profile. Then we get our solar radiation in. This heats up the whole water layer over a specific depth. And of course, it heats up the first layer more than the second layer. Then we have cooling at night going on. So we have evaporation, evaporative fluxes. So the first layer cools down now. So the red line is also, as always, the current temperature, and the solid line is the temperature of the previous day as a comparison. So now we have a cooling going on. So now the first layer is more dense than the second layer, which of course should never happen in reality. So then we have convective deepening happening first. So these two layers are merged together. Afterwards, we have wind steering. So the wind also affects the whole surface layer over a specific depth. So now everything is mixed for these three layers, which have now changed their thickness over time. And now we have like these three main layers happening here. And now we have shear stress happening as the final energy or the final iteration step. So now we have two big layers. And now if this system here at the thermocline is still not very stable due to shear mixing, we have so-called Kelvin-Helmholtz mixing going on. So then we have, or GLM creates lots of small layers to have like a more fine representation of the thermocline. So this is how GLM surface layer mixing happens over time. And you can really see how beautiful this Lagrangian approach looks like.
I agree, Robert. It is beautiful. And somebody who's an ecologist who doesn't understand lake physics in any kind of useful detail, this provides physics, in a box, along with, consultative services that you provide. We can actually come up with a really good physical simulation of a lot of systems. Maybe not all, but
yeah.
Mm-hmm.
So Robert, a quick question. So all of these steps are happening within each hour in the model space. Is that what you're saying? Like sequentially?
Between each integration step. So if you have T1 and then you integrate plus your 1 hour mostly, then this happens sequentially in this 1 hour.
Cool, thank you.
At least this is how I understand the code. So be cautious what I say. I also have this small animation to show you how it looks like in GLM. So on the left side is the theory. So the first layers are mainly affected. The surface mix layer thickness is mainly affected by the wind and the convective overturn, as shown before. Below that, you have all the shear instabilities, and at the bottom, you also have steering by the sediment. And here's a small, really nice animation, or actually a simulation about Kelvin-Helmholtz instabilities, which are just like a strong shear mixing between two layers with different velocities. You can see it starts really small, and then the eddies are forming, get a lot of mixing going on between these two layers. And here is an actual GLM output simulation. So the left the left shows you all the different volumes over depth with the thickness, and also the temperature corresponds to the color here. So red is warm and blue is cold. And here you can see actually how it looks like the vertical profile. So you can see now it's like 8 p.m. So now convective deepening is happening. It gets lower. The thermocline is now here. And now the next day, and then at night, it's always like deepening the thermocline. And at day, it's heating up the surface layer. So this really shows how GLM works more or less over the course of a day if you use hourly data. Okay. Any more questions about mixing?
So Robert, I've just joined like halfway through your presentation, but maybe I can ask a question and you can, don't answer it if it's sort of obvious or something, but you've got this benthic momentum and stirring going on at the bottom. So is there an actual flow? There's no velocity, right? So then how is that kind of
It's represented more or less by a shear stress caused by like a power law over the sediment.
Okay.
So this will mix up like the whole layer close to the sediment, which then can move upwards and downwards a bit. So you have like small shear stress originating from the sediment going upwards.
So is that related to like the wind, or how does that get activated?
It's more or less because you have like this stable sediment and you have something moving above it,
Yeah.
which is like this, what's called benthic layer mixing.
Yeah.
But also in the model, you have like internal waves, which can also go down and
So,
adding energy to it.
okay, so maybe it's the waves, kind of internal waves.
I think it's actually both. I think it's internal waves going down, but also there's this benthic momentum drag going upwards, just because you have this stable layer at the bottom. I don't know how strong it is, but
Robert and John, tell me if I'm interpreting your question. So in implementing the 1D model, Robert, especially in the case of a reservoir where, for example, you're going to have inflow events, you know, that water movement or flow across that boundary layer would create, you know, mixing. And yet this is a 1D, a one-dimensional model where everything is averaged horizontally. So how does that sort of transfer of that inflow energy get implemented within GLM to change those dynamics? Was that about right, John?
Yep. Yeah, that's good.
Okay. I mean, inflow is a different term of energy. So inflows also go into the model, and then the inflow comes in into like this layer of neutral buoyancy, and then you add or create a new layer there, which then also mixes to the shear stress afterwards. So the more inflows you add, the more complex the model ones also get. But this, I think, is mostly here on the right side. I hope you can see the PDF from Matt Hipsey, 2019. And here's the deep mixing. It's only like 1-page explanation. And this is like a really good source to follow it up.
Yeah.
But this is a really good question. So I just know from some models that the benthic steering is really powerful in mixing it. But also it's like this mix of the benthic sediment and internal waves going down the energy. But yeah, it's a good point. I don't know which one is more dominant. Yeah, thank you. This then brings me to the last slide for the introduction. So GLM applications. So GLM is used in a lot of different ways, a lot of different projects. So here you can see, for example, climate change effects on lakes. So from Huang 2017. So where you can see temperature increases in the surface layer and you get more stratified days per year over time. And here you can see also GLM was used to predict in the future the change of ice cover shifts or the probability of ice cover. So here they used an ensemble of models to show the current probability for ice and the future one, and they all predicted a decrease in the future. And here GLM was like the most conservative prediction, which shows you that it's really good to use an ensemble approach. And also you have projects like the smart ecological forecasting, which I think is also a big part of this workshop here. And you also, GLM was used in a lot of management applications, for example, for reservoirs to find the optimal withdrawal depth to not pollute the rivers downstream with too much or too high temperatures. Okay, so this is like the first step of what is GLM. And on the second part would be setting up and running GLM. But if you have like more questions to GLM in general, then now is a good time. And otherwise, I'm still thinking in my head about the deep mixing because it's like a really interesting topic. But yeah. Okay, if not, I can continue how to set up and run GLM.
Good. I'll keep an eye on people.
Thank you.
See if they have questions.
So I will talk about installing GLM, which is always a nice example. Then what is the main configuration file? What else do you need? And how can you use R for it? So there are 3 main ways I normally use to get GLM. Either you can download a precompiled binary from the website, or you can also download the source code and compile it yourself, which is more or less easy in a Unix system and a bit more tough in a Windows system. And you can also get GLM inside of R if you use GLM 3R. And also the website of GLM is like a really good source if you want to know more about the model and how it works and which parameters you can use. So the main file is the glm3.nml, the name list file, which is the configuration of your lake model. So this has like these small blocks that always begin with the and symbol and end with a /, and they are organized into specific topics. So for example, the setup, the mixing coefficients, and how light is handled. And they also include the relative paths to the water quality and the driver data. And your GLM executable needs the setup file to run the simulation. So in this file, you should do a lot of different things to really represent your lake in the simulation. You should define your morphometry of the lake, which is the keyword morphometry. And here you have the area depth relationship, so the hypsography, so the area over depth, which is also the keyword H and A. Then you also have to define what you want to simulate. So for example, your state variables, temperature, salinity, and also water quality, your quit resolution and time step. Normally you don't have to look at the quit resolution because it uses flexible approach, so it will change over time. But sometimes a lot of problems are also due to this Lagrangian approach where you have to change your maximum allowed thickness. You also have to change your time steps, so how long do you want to run the simulation? And because it's a numerical model, you also have to give it boundary condition data, so inflows, meteorology, and outflows. And you have to provide an initial condition, so your initial profile. And then you can start the simulation.
Quick comment, Robert. I'm not going to show it for the biogeochemistry, but within GLM, that second line which says water quality setup, if you indicate water quality setup, then there's an additional file, at least, probably 2 or 3 other files, in which you have a similar kind of set of things that need to be defined to make the software run correctly. So again, just to reiterate, this is for GLM, the physical modeling. The water quality simulation is a whole nother set of files that are similar in concept.
Yes, thank you.
Yeah.
That's a good point, yeah. So AD is like an additional file, at least one.
Yep.
Okay, then what else do you need? You also need AED files if you want to simulate water quality, but you also need your boundary conditions data. So at least you need the meteorological data, either with an hourly or daily time step in the CSV format. So you need your radiation, your air temperature, humidity, wind speed, and rain. And also if you have it, you also need your flow data, so inflows and outflows, also hourly or daily, and also in the CSV format. So like time, flow, temperature, and salinity.
And another quick comment, in ecological training, unless you're involved in some modeling projects, we often don't talk about boundary conditions. But I think a very simple way to think of it in this context is if you drew a picture of the lake and you were measuring everything on the inside, the boundary, generally speaking, is what's outside of your picture of the lake. So it's going to be meteorology, inflow, and in this case, probably the sediment water interactions. And those things force the physical dynamics of the system. Right?
Yes.
If I got that right.
Yeah.
Okay.
And yeah, the next thing is if you are an R user, then you're really lucky because you can run GLM in R. So we have this trinity of packages, which maybe I shouldn't call trinity, but it's a good keyword. So first you have GLM3R, which is like the base package. If you download this, you can run GLM in R. Then you have GLM tools, which you can use to change the model setup, visualize results, calculate physical derivatives, and calibrate the model now. And on top, you have Quepler, which is gives you access to a distributed computing system, so you can run multiple GLM simulations at the same time on someone else's computer, and you can do like really good scenario assessment. But there's more. There are a lot of more cool R projects for GLM. You have the macrosystem eddies, so to teach about macrosystems ecology. You have Lake Ensembler, hopefully soon, which is an R package to run lake ensembles. So currently there's not only GLM, but also Gotham, Simstrat, FLake, and MyLake. So you can run 5 lake models with the same setup of data. And we also have Columbus for Limnology, which is an online platform which allows you to run GLM online in the cloud using containers. And hopefully you can also do some R calculations also in the cloud soon using GLM at this website. So there's a whole workflow approach about using GLM with R.
Robert, a quick question. I think it just popped up from Rachel about evaporation. Is it estimated from long wave, short wave, relative humidity, or what?
It's the saturation between the humidity of the water and the air. Is it the right word? Sorry, not saturation. It's the evaporation flux is this classical representation using this one value 0.0013, and it's not the humidity. What is it called? I'm sorry.
Vapor pressure?
Yeah, what's it called? Sorry.
Vapor pressure?
Yeah, the vapor pressure between the water column and the air times the coefficient, which then is the evaporation at the end. Yeah. So it's here.
Okay.
This equation on the right side.
Great.
Okay, but it's estimated from other like forcing parameters.
Oh
that
yeah,
are
so you have
provided.
the wind
Okay.
speed and times the vapor pressure.
Yeah.
Yeah.
Okay.
Yep.
Thank you.
Yeah, I always have a hard time to get in my head right what is the sensible and what is the latent heat flux, and then the symbol. But yeah, that's my problem. Sorry, that was a too long answer.
It's good.
Okay, so
Yeah, I was just curious of how it was handling that. Thank you.
okay, so the next thing, so GLM tools is the thing I want to show now in the workshop. You can install this either from GitHub or from Quan, which is the USGS version of Quan. It gives you like a different options. You can manipulate the setup, retrieve output data, compare data, and visualize data. And now since last year, you can also do this really beautiful GG plots. So this is like a really nice package now. And now we can jump into R. If there are no more questions about lake physics or name list files. Okay, awesome.
I have a question, Robert, real quick. So do you typically edit your like boundary conditions or model parameters in your name list file, or would you do that using GLM tools there?
Do you mean like the inflow data?
Yeah, I was just looking through the name list file and it appeared, yeah, like inflow data, but also like parameters and everything like that.
I think I know what Nick's asking, if you don't mind me jumping in, Robert. So the files that are needed to run the simulation include a bunch of configuration information, which is in what's called the name list or NML file. And that's what Robert has set up right in front of us now. In that name list file, it indicates what are the input data. And in this case, he's highlighted the inflow data. And those would be separate text files that are configured a very specific way so that GLM understands how to read them. And so when you're running simulations to fit historical data, you find your historical inflow or meteorological data to make your predictions about your lake. If you want to run scenarios, you can either get scenarios of changing meteorology, or you can make up your own meteorological data and see what happens. Did that answer your question?
Yeah, that definitely answers my question. And I guess I was also wondering, like, so if you have like something like you said, there's like a mixing coefficient or something that I'm thinking of as more of like a static parameter within your model, but say you wanted to vary it, would you typically do that within these name list files?
Yeah, I would do it in the name list file before I start if I have like a good approximation or assumption for it. Otherwise, I would leave the default value if I don't know what I would expect, or if I'm really sure. I would also try to calibrate it if I'm really sure that it could be sensitive. But calibrating, like, I mean, most of these parameters are like from empirical field studies. So there's like a range between them you could calibrate. But in most cases, it's always hard to calibrate too many parameters because then you have like the same configuration with the same results, but like different high and lows. Like this equifinality thing, where a lot of different combinations give you the same result. So
Yep,
it's hard
yep.
to do like a big calibration. So I would always like leave most at the default value and hope for the best.
Yeah, yeah, thanks. That answers my question.
Great. Another quick comment, especially given the context of forecasting that a lot of people here are familiar with. It's important to realize that the typical use of GLM, AED, and what we're showing today is that you set up your parameters before you run your simulation, and you say go, and those parameters don't change. Even if you're running a simulation for decades, you end up with the same parameter values. That's a really different concept than what's implemented in what Quinn and others have developed for forecasting, which is to recognize that the model is just an approximation of the system, and sometimes it can be really helpful to change those parameters through time. But that requires special sort of environment and programming that has been set up by the whole FLARE project. So that's a pretty unique it's a pretty unique environment for GLM. The concept of changing parameters through time has been around for a long time, but recognizing it's a pretty big and complicated piece of software, implementing that within this environment has been a very large task.
But to accomplish that, though, it's all done in the same context that Robert and Paul are showing you, where embedded in all the FLARE R scripts is basically editing this NML. It looks for the variable name for the parameter that you're trying to that you're calibrating over time, and it just overwrites the value in there, and it updates NML, and then it executes the model, and then it yanks out the output like they're going to show you. Everything else is just wrapped on top of it, but it leverages the entire kind of GLM framework that you're being shown today.
Okay. Yeah, that's a good transition to R. So if you, now we can jump back into finally some coding exercise. Which I hope you all did download the example file. So this is like the GLM setup. You have a nameless file, you have an AD file for water quality, and you have our boundary conditions. So you have field data observed from the field, your meteorological data, an outflow, and 2 inflows. So this is Lake Mendota. So we have the Pheasant Branch and the Yahara River. And so in this case, first thing you should do is change your working directory to your path on your system. Then we need the good old GLM tools, GLM3R. You also have to install GLM3R before installing GLM tools, because GLM tools depends on GLM3R. And some other packages I need to use because of my sloppy code. And then if you run this first line first, you can see that's now using version 3.1.0b1. So so this was just changed like 2 days ago, no, yesterday, sorry. So it's like the most recent version, which is also now available at GLM3R for Mac, Linux, and Windows. So the first example is to calibrate just GLM, so only the hydrodynamics. So first we give a path to our nameless files, our configuration file. And also we just give a path to our output file, which will be created soon. So the output is the results from the simulation. Then also a path to our observed field data. Then because we want to calibrate it, so we want to overwrite our nameless file a lot of times, we just copy it. So we don't destroy our original file. And then we also give a path to our nameless file, which was now just created. So the first thing is you can just run GLM really quick. So this takes like 5 seconds, 3 seconds. So it's only, I think, 6 years and only hydrodynamics. So next thing is you compare it to our temperature data from the field. And this looks like this. So not too bad. You can see, I mean, this is what you expect from a lake model, that at least it can replicate temperature dynamics.
Robert, can we pause for a second and take a look at especially the upper panel, which has all the dots in it?
Yeah, sure.
Yeah.
So all the dots are monitored data from the field.
And so the heat map is interpolated from all the dots, right? in the upper?
Yes.
Okay. And so that's the observed, and then the model is on the bottom. Yep. And we see pretty good correspondence. Some differences, though, for sure.
Yeah, but this is also now not calibrated. But I mean, you can see the model also works without a tough calibration process.
Mhm.
So the next thing would be we can look at the root mean squared error between our observed data and simulated data. So this is the next line of code, also from GLM tools. And this gives us an RMSE of 2.87 degrees Celsius. So for all points. So for all points over time and all points over depth, and just compare all these points between the observed data and the model data. And it's not that good, but this is also now uncalibrated. So what we did at last year was an automatic calibration approach for GLM in GLM tools, which I now slowly want to go through in the next slides. So first, at the moment, it only works for temperature. So we have to give it the keyword temperature, then our current path, then also again, the nameless file, what it's called. And then we have to look at what we want to calibrate. So here I just did too much. So I want to calibrate the wind factor, which multiplies our wind velocity from the Limnology data. Also the long wave factor, which is also a multiplier for our long wave radiation. Then the CH is a multiplier for our sensible heat flux. Then also we have two sediment layers in the model. So they heat up the bottom of the lake and the top of the lake. And we also want to calibrate which temperature they have on average. Then this one is a coefficient for bottom deep mixing. So this is like the base value for the diffusion coefficient. And you also want to calibrate the light extinction value. So at the beginning, we have the initial guess of 0.3. So
I pause you.
Sorry.
Yeah, let me pause you for just a second, Robert. So assuming I understand this correctly, the goal is to make temperature represented in the model in the bottom panel on the right be as close to the observed as possible. And the way to do that is to take a bunch of guesses at parameter values that might affect things like mixing in the system and water clarity in the system. And those parameters are located within the GLM nameless file. And the software you've written is going to go through and take a bunch of guesses at those parameter values and try to find the ones that give us the best agreement between the top and the bottom, right?
Yes, yeah.
Okay.
So this is using an automatic calibration approach called CMAES. So covariance matrix adaptation evolution strategy. So it will get better over time if you want it a lot of times. So ideally, you would want this like thousands of times again and again to get like the best approach. And you would also take hopefully less parameters in this. So this is just like an extreme example to show how the script would work in theory.
Yeah.
So then you can also give it like a GLM command. So if you give it null, it will use GLM 3R, but you can also give it the path to your own executable of GLM if you have that. This allows you to use different versions of GLM or also your own modified version. A first attempt is just telling the script to delete everything in the folder which it created in the previous one. Then we did this to show you that we also have a calibration validation approach. So this line of code will take our observed data and then split it between a calibration and validation with a ratio of 2 to 1. So calibration 2 to 1 validation. So we have a total time period going from 2009 to 2015 and a calibration going only for the first 4 years and then 2 years for the validation. So the model will only calibrate the calibration period, but will also give you the results for the validation and the total time period. Then we also scale all these parameters because they have different units. So we scale them off in a space between 0 and 10, which makes the application of the optimization algorithm more smoothly. Here we're using as I said, an evolutionary strategy, but you could also use nilder-meet as an optimization algorithm in this case. We want to optimize the RMSE between observed and simulated data. So currently it's only available as an option, the RMSE here. And then the target fit and the target iter tell you how long it should run or if we want to stop it earlier. So a target fit of 2 means the simulation or the optimization stops after having an RMSE of 2 or below. And the target iter would tell the script that it should stop after 20 iterations. But ideally, you want to run this like 1,000 times or more, if you have that time. We don't have that today, so I'd go for 20. Plotting means you want to plot the results, then you just tell it again, output files, field data, and then you run it. And it gives you this nice warning that everything is under development, so don't trust it too much at the moment. And then it runs GLM a lot of times. Like Quinn said, it changes now the parameters in the name list file. So it did create a GLM3 file, which is now changed again and again with new parameters. And hopefully we get an improvement. So we start with 2.8. And yeah, normally 20 is not enough, but it takes some time to really get to a gradient going downwards. So hopefully we get something below 2.8 in 21s.
I already saw a 2.65.
Not too good, but at least the right direction.
But it's better, right?
So it will give you a lot of different plots. At the end, you get a diagnostic plot. So you can see your residuals over time against model values, over depth and everything. So you can really look at how your model performed, at least. And also you will get how it went down. So the first guesses were here at 10 and it gets slowly down, but yeah, close to 2.5 at least. And we'll also give you some heat maps. So for the calibration period, we got 2.67 after 21s. For the validation, only 2.77. Not too good, not too bad. And for the total, we get an RMSE of 2.67. So we improved it a little bit, which is, yeah, a good thing. Okay, so this was the first example for the calibration of just AED and how the GLM tools can really help you with doing it in an automatic way. The next example would then go into water quality. So we can, if there are no questions, we can just now go into our GLM3 file and add, because at the beginning we just calibrate only GLM without any water quality. So we have to add our water quality setup to it. So now we can run an AED file with oxygen, phosphate, nitrate, and so on, dynamics. And there's a big discussion, at least what I understand now, if you can use automatic calibration techniques for water quality at all, or if it's just like too complex. And there are like two papers, me 2020 about an MOM simulation and also Limnology 2019. And they both argue that you shouldn't use automatic calibration algorithms for if you want to calibrate water quality because of too many non-linearities. So first,
well, I can follow up on why they concluded that. That seems that they're just throwing their hands in the air.
Yeah, totally, yeah.
And I mean, there seems that there could be a solution around that.
I agree. Maybe we don't have the right objective function to use them also. We don't know what we want to calibrate. Maybe the RMSE of all these things is not the best approach, the simplest one. But at least these papers now argue that you should use your expertise knowledge for these values and not calibrate too much.
I mean, like hierarchical Bayesian methods have been used to calibrate nonlinear models for a while. So I don't know, using likelihood as the, likelihood times the prior. So you have some expert knowledge in there, but in a more formal way that just doesn't throw its hands in the air. Yeah,
I mean, that's a good point. I mean, I agree that there is a solution, but at least these recent papers and also my experience with like Lake Mendota shown that it's really hard to use at least like these evolutionary algorithms for that with just RMSE, but there should be an approach to that if you really want to calibrate all these things. And maybe also using a system metrics, not only like time series, but like how the ecosystem responds to it.
But also, I mean, if the parameters are viewed as having distributions rather than a single value, which I think is what this kind of determines, and viewing them as covariant, where there's a, parameter A can be high and parameter B can be low, and they'll give you the same answer. Viewing it from that perspective might help deal with some of these nonlinear issues. Because there are trade-offs in parameters. You won't get the same answer every time when you calibrate. If there's you have to know whether parameters are identifiable in the first place. Because two things multiplied by each other can give you the same answer.
Yeah. Yeah,
in
yeah,
different
totally
ways.
agree. Yeah.
And just to comment a little bit further, if you're new to simulation modeling and you're imagining setting up and calibrating, especially GLM AED, to include the biogeochemistry, this is a pretty huge issue. This is one reason why we're putting time and effort into various approaches to calibration and training, because it can take it can take somebody 6 months to a year to feel really comfortable with having GLM AED set up and representing especially the water quality aspects of what's going on. And knowing that science runs pretty slowly as it is, it can be pretty frustrating sometimes to, have to set aside that amount of time. So on the other hand, I think those who go through GLM AED find it's almost like taking a small course in limnology and modeling combined. So you end up learning a ton in the process, but you do pay for it with time for sure.
Yeah.
Something else that's really important is that using these automated tools, because given that at least in the past year, there's been 7 major GLM updates and each one requires its unique calibration that you can't hand tune to do this efficiently.
Yeah. Yeah, I mean, yeah. I think we need more research if you want how to best calibrate water quality in general. And I mean, people give up, or some people give up nowadays, and I think you can't blame them most of the times, because it's like a really tough subject, and mostly it also works really well with expertise knowledge. So if you have like a good guess for the parameters from field data. But for here, we also now not using an automatic approach, because at the moment, our lake analyzer and GLM tools only or mainly deal with the physical side. So they, at the moment, they don't work for water quality. So that's why in this code, I added some custom-made functions, thanks to Time Moore. And which will just read in the observed data. And now we try to look at oxygen in this example. So first we can plot our simulate oxygen over depth and time. So you can see here we have anoxia and a hypolimnion happening every year, at least in the simulation, which was now calibrated. And if we compare this now to our observed data, it looks like this. So our modeled anoxia is too low compared to our observed anoxia. So we have to crank up our depletion rates in the model itself to get a better representation. And you can either do this by increasing the sediment sink of oxygen, you can increase the mineralization, you can add more phytoplankton and hope they disease or decay really fast. So it's a lot of different things you could improve now to get to the same result.
And that's, yeah, and in some ways that's kind of the crux of the problem, right? Which is, your observations and your model aren't matching. It's a complex system that includes physics, chemistry, and biology. And where do you turn? How do you know where to go to start tweaking the system? And you also do have this question of, is it your driving data or is it the configuration of your model too?
And also you have to know about all your phytoplankton groups that you can expect and also all your zooplankton groups. So it gets more complex.
Yep, I mean, and anytime you add biology, it gets challenging for sure.
And in some cases, you forgot to add a third one, Paul, that that there's a bug.
Oh yeah, oh yeah, and we're not talking about the animal. Yeah.
Robert, I have a quick question for you about the calibration exercise that we just went through. Which, sorry if I'm a little slow to process my question. So when I'm running the calibration, it'll give me a couple of calibrations where the RMSE is like pretty good. You know, it's like 2-ish, and then it'll be like 8, you know, for the next iteration, and then it goes back down. So what is how is that happening, basically? Like, what's going on under the hood with that?
I mean, this is like maybe a longer answer to the question. So at the end, so it's using like distribution functions normalized over all the dimensions of the parameter space, and then it moves down to try to find the minimum of all of them. So it's like this covariant matrix approach, which I have really hard time to explain.
Yeah.
But I have some other presentations where I did some animations for that, how it works.
Mm-hmm.
But essentially, it's using like different generations, and then if you have like different 20 populations in the same generation, and the best one can reproduce, so you can also have like a random chance of getting worse results in the next iteration compared to the first one. But hopefully, if you run this a long time, it should go down with the RMSE over time. But you have like sometimes like these bad results in between.
So it just doesn't, it's kind of testing different areas of that covariance matrix. And sometimes it in that testing process, it's jumping to an area where it's like, oh yeah, never mind. That was not the direction we needed to keep going. Let's go back.
Yeah,
Okay.
That's the thing, yeah.
Yeah, that's right. And I think you can visualize a landscape that has lots of valleys, and you're trying to find the deepest valley, and you're starting to go down one that you think is deep, but you should once in a while randomly jump out of there and just check some other place to see if it might be a little bit deeper. So this works for so many things. Every good search algorithm should step out and check some things randomly. You know, whether you're looking for hiring people or optimizing GLM.
That makes sense. Yeah, that's kind of what I thought, but I will also, that's helpful. Thank you.
Okay, yeah, thanks. I mean, that's a good question. I mean, yeah. But just because we only have half an hour left, I'll just continue. So in this example for oxygen, we don't use automatic calibration, so I just do some permutations of some results. So I just want to change the sediment demand of oxygen, the half saturation coefficient of oxygen, and my mineralization rate, so how fast bacteria can decompose my DOM by using oxygen. So I want to change these 3 parameters stepwise at the same time and just see what sticks at the end. So I permute them. I'm just using like, I want to change the first value, the sediment oxygen demand like 3 times, the half saturation only like 1 time, and mineralization only 2 times. So I get 3 times 1 times 2, so 6 model ones. I just want to see which one gives me the best RMSE compared to my observed data. I mean, this is just like giving you a really fast example how to do this in R in an easy way. But of course, it makes sense to run this or to do like a big sensitivity analysis for a bigger project, or even thinking about a better objective function to calibrate this. And maybe here a Bayesian approach is really the way to go. So here I'm just now running the model. Oh, that's way too fast.
Oh, did you not copy in the water quality code?
I did copy it in because
okay.
I got this, but
oh, right.
Sorry for that. It worked yesterday. That's okay. Something is not happening in my code. So this is way too fast for water quality. It should take up to like 15 seconds. Is it working for anybody else? Did anybody try that?
Mine seemed to work okay. I was able, it took probably a total of 5 minutes to get through everything.
Okay, so that's reading nameless, so Plankton, there was an error. That's a bummer. I don't know why this didn't happen yesterday.
That's okay.
This would just be like a bit bad if I want to show the next examples. Oh, yeah, sorry. This must be false. Here it's true. Okay, so if you want this,
Zooplankton don't matter, right? Did we conclude that at some point? joking.
Right. But yeah, I know. Zooplankton, we don't understand very well within the modeling world.
They're turned off in Flare. That's why.
Oh, okay, really? That's good.
Yeah.
Heather's going to turn it back on. That's chapter 4.
So sorry, I did have to add this yesterday because now they are on as a default value, which is affecting my simulations. But okay, now it's working, so it's really slow. It will take a long time to run. So now zooplanktons are on by default in the newest version of GLM 82, and they're too high in the current simulation, so they will eat up everything.
Whoa.
But
Is that the reason why you were seeing crashes in your Phytos?
Yeah, but I also see crashes in the Phytos when I turn them off.
Okay, never mind.
I don't know why, yeah. But now it should take a normal time to run, hopefully. Oh, I did test this like 100 times. Yeah, 4.8 as a new RMSE, so this was like a really bad guess. I think we had at the beginning an RMSE. Now I have to 3.4. Yeah, 3.42 for oxygen, and now it's 4.8. So this definitely didn't improve our results. So if you have like good guesses, you can run them all and see what sticks, or take a better approach. So this is just like showing you a really fast example what could work. And I really hope this is now continuing to run. 4.7. Okay, so all my guesses are really bad. Yesterday it was improving. So yeah, we didn't remember when we did this workshop last week. We used the last version of GLM, and now yesterday with the new version, somehow it changed the AED setup, which I don't know why. Maybe it's just like because we didn't investigate enough to see what was changed as default values. But normally it's not that drastically that the whole model changes a lot between these smaller releases.
Robert, I'm going to step away for just about 2 minutes, take a quick break before we move over to biogeochemistry, okay?
I have one more example, or?
No, keep doing your thing.
Oh,
I'm just saying I'm going to step away.
You step away, okay.
Yep.
Are there more questions until the script finishes to run, or I can also try to stop it and see if this works?
I'm just excited I've been able to follow you so far because my current repositories were all kind of messed up. So thank
okay, that's
you.
good. Thank you. That's nice to hear. Okay, this is taking too long. Oh, 3.31. This is like, wow. Something is happening in the right way. So if you run GLM only, it's really fast. If you couple it to 82, then it takes a longer time to run.
So Robert, while this is running, how do you go through the calibration process? We have a pretty big project on long-term dynamics of anoxia that you'll show some results for over 37 years. And there was a lot of calibration activity that went into that.
Yeah, for this I used an automatic calibration approach, the CMAES algorithm, for all the parameters over hundreds of times, several times. And at the end, I also manually calibrated some AED2 values to get like a fit which makes more sense looking at literature.
Yeah. I think, say if I were, thinking of spinning up a GLM simulation that included biogeochemistry, this could be pretty intimidating because there's a lot that we're going through in a pretty quick period of time. But I do think it's reasonable to say that if you go with the default values for the parameters, you end up with pretty decent approximation of what's going on in the system. Do you think that's true, or sometimes the systems are just so different that it's just going to take a long time to go through that?
I mean, that's a tough question. Yeah, I mean, for AED2, the default parameters can be challenging. For example, if you look at the online website, some parameters as default value doesn't make much sense. So for phytoplankton, there are some groups which are called N-fixating, but they don't fixate N, nitrogen, in the online database sometimes. I mean, you still have to play around with it and to understand. And my personal opinion, simulating functional groups is always hard because you want to have like this big group which represents all of cyanobacteria groups, which is always difficult in a conceptual sense also. I don't know what the best way is to approach this. So currently we are doing this lake ensembler project in AmonJ, which is a Eulerian network for modelers. And we really hope we can do some benchmarks on lakes with water quality models and to see what is like best approach, how we can change parameters.
And you're modeling phytoplankton, zooplankton as well, or no?
In Lake Mendota, yes, and the lake ensembler, not yet.
Okay.
So we were really lazy and started with the physics because that's easy. But with the biology, it's like really hard.
Yeah.
It's like the saying, right? Ecology is no rocket science. It's way harder. Which I think makes total sense to me.
Yeah.
So this will be finished hopefully in next one, and then we can continue. So hopefully it proved the oxygen fit a bit. Yeah, so now we will take the minimum value of these RMSEs and just go with that. And then if you want again, and hopefully this plot will improve in a second a bit. And then finally, afterwards, I just want to briefly mention how I think is the best approach to calibrate phytoplankton. So for the phytoplankton, if you're running AD2, you have a lot of different variables which you can change. I hope you can see that. So for example, you have cyanobacteria and diatom. So you have two groups, and you have all these values which you can change to the best of your ecological knowledge. And sometimes you just play around with that. You change one, and you hope something happens. And last year I talked with Matt, and at least he recommended me looking at limitation functions, which I want to briefly explain here.
Could we go back to that NML file just really quickly? So sometimes the question comes up, how do you define what an organism is? I mean, do you go in and you say a diatom is this kind of organism that has this, kind of physical shape and exists in this particular way? It's a little more rudimentary than that within the simulation environment. Phytoplankton, as well as anything, I guess here, any state variable is represented by a suite of parameters. And so what you see on the screen define what cyanobacteria are and what a diatom is in the case of simulation. And so a diatom, if we look through some of those parameters, is going to have a different sinking rate than cyanobacteria. It's going to have a maximum productivity rate that's higher. It's going to have a different respiration rate than cyanobacteria. Cyanobacteria are going to manage their organic carbon and their phosphorus a little bit different from diatoms. And so these are the characteristics that define what species are within the modeling environment. And you can imagine there's, I don't know how many are there, but roughly 40, about 48 different parameters. And do we really know the difference, among species with respect to those parameters? I think pretty hard pressed to say yes. So it's one of the great challenges in modeling biology in a system is trying to know what from that parameter suite is important to change.
Yeah, definitely. So, yeah, that's a great point. Yeah, so it's complex.
Yeah. Yeah.
As you can see here in the R results, oxygen was only improved a tiny bit for 2010. The other years not as much, but still you can play around with that and to see if you can optimize your calibration. So I want to briefly mention the phytoplankton problem. So here we have like some bacteria and diatoms. So they currently unfortunately look like this and nothing is growing at all. And okay, there's some diatoms growing in the bottom of the lake, which I don't know why. So in the last version, they were really growing at the top in spring and now they're at the bottom. So I have to investigate what's happening now. But for example, now you want to know, hey, why are they not growing at the top? So you can look at the limitation function. So now in the output file, you have a limitation function for light, for nitrate, phosphate, silica, temperature, and salinity. And you can actually plot them as contour plots. And this just takes a second. But if you do this for cyanos, you can then see, hey, they are not growing there because of that, which will pop up now. Or, oh, sorry, it's the next line of code. So if you do that, at least I think this is really helpful for me to understand why it's not growing. So here you can see at the top layer, they are growing here. So 1 means they are not limited by light. So they're growing up to here at this depth, which I think is way too deep in the simulation right now. So they could grow up below, up to 20 meters. So something with the light attenuation is not working as I want it to work. And they're limited at the top by nitrate and by phosphate, which I don't know why. There's no limitation for my cyanos by silica, which makes perfect sense. And they have like a really good time at high temperatures at the top, which also makes sense for some bacteria. And there's no limitation by salt because I have no salt in my setup.
Okay. Cyanobacteria like hot moments, it looks like, or hot temperatures anyway.
And the same is also can do for diatoms. And if you look at these results, then you get understanding why your bloom is not happening in spring because the temperature maybe is limiting. So you can see from my diatoms in the temperature, they have a good time also in summer, but maybe I have to decrease their optimized temperature a bit to get them also like having good time in early spring. Or I have to increase at least my nitrate values to make them grow more. So you can really look at these contour plots to understand what is actually limiting their growth.
Robert, this is really cool. And I don't think these functions existed the last time I was really playing with GLM. When were these developed and by whom?
The keywords were added last year, October by Matt, I think. And yeah, they're really nice to have. They're really powerful. And you can also look at depth-specific results. You can just plot your thermocline depth and understand why nothing is going there. And then you can see, oh, I have no phosphate.
That's so helpful.
Oh, it is. It's better than just randomly changing parameters, I think.
Mm-hmm.
Okay, so this was the calibration, the 3 calibration exercises. So should I just show now the screen for the water quality poll, or do you want to share?
Yeah, go for it.
Or do you want to share your screen?
Oh, yeah, actually, let me share mine. So if you unshare, that'd probably be good.
Yeah.
Okay. And bear with me. This might take me a second.
And sorry, I took a bit too much time.
Oh, no, it's all good. Okay, can you see the slides?
Yes.
Great. So we'll talk a little bit about biogeochemistry, which is a big topic, of course. And, there's no way we can cover everything that GLM AED does and how it does it. So we'll focus on oxygen and carbon as an example, specifically because of its relevance to FCR activities and the kind of research that's going on right now within the group. First of all, available modules, I'd encourage you to go to the AED website. There's a lot of really good information there. I would say it's probably not as complete as we'd like it to be, but at least you see all the equations, you see a lot of the parameter definitions, and you see, availability of different components of the software. There are a lot of different modules that are available for GLM, and some of these I've never used. The ones that we do use include oxygen, inorganic carbon for which includes carbon dioxide, methane, phosphate, of course, nitrogen species, and phytoplankton as well as the organic matter. But there's a lot more there that we don't use and that's available to you. It does sort of beg the question from a modeling perspective, though, of if you're implementing only some of these modules some of the time, what's happening with the parts of the system that you're not modeling. And it's sort of a whole topical area of what does it mean to have a more complex or simple model. But do keep in mind that as you add and remove different modules to the setup of the software, the calibration does tend to change because you have different processes that are involved in the modeling activity. This diagram taken directly from the website from Matt, I just want to show a few points here. It's a fairly typical setup of AED, the biogeochemistry. We've got particulate organic matter, dissolved organic matter, oxygen, inorganics. We've got some phytoplankton, maybe zooplankton as well, and it does show sort of the boundary conditions of the system. Also, I want to point out what Robert said earlier, that this is a mass balance system, which means that all elements that are explicitly tracked are accounted for throughout the system. And this turns out to be really important. So in other words, you cannot gain carbon, you cannot lose carbon unless it enters or exits the system through one of the boundaries. You can transform carbon among the different pools. This turns out to be really handy from a modeling perspective because it provides a lot of stability to the system. It's really hard for things to go way out of whack because you run, for example, out of carbon. And it has built-in controls to make sure you don't go negative, for example, in carbon. But it also means when you use the mass balance approach that it's really hard to reproduce certain kinds of dynamics of the system. It's hard to reproduce biological activity. So, how would you move organisms through the system? You can move them up and down vertically because it is a vertical one-dimensional model. But of course, there's no horizontal movement biology through the system. Also, phytoplankton, for example, will tend to aggregate and disaggregate in ways that aren't represented well in the model, creating really high sort of nonlinearities in the system. And then finally, the time scale and space scale at which the model functions means it works particularly well for certain applications, but it's pretty challenged in other applications. We had talked very briefly before about disinfectant byproducts. And one of the difficulties of using something like GLM AED for modeling DBPs is that the concentration of organic matter in the system that we're tracking through time may be 1 to 2 orders of magnitude higher than DBP precursors. And so we think we're doing a pretty good job in getting the organic dynamics through time. And the precursors are just kind of bouncing around in the noise level of what we're actually modeling. And there's a pretty big scale disconnect between what's happening. That goes the other direction too. If we want to take a GLM AED that's calibrated for this year and run a simulation for a decade or a century, we might expect pretty big divergence between what we're modeling now and what happens in the future. So just like with all modeling activity, scale, thoughts about scale, both in time and space, and how you're applying the model and the questions that you have are really important. I want to look at a very simplified example with respect to carbon for how the model works. And here we'll focus on dissolved organic carbon. DOC in GLM AED is modeled by 2 different pools. The recalcitrant pool, which is this sort of darker brown. And then I've gone ahead and put L for a labile pool of the DOC that's here. Within this kind of modeling environment, there are kind of 2 essential components that are helpful to think about, the boxes and the arrows. So the boxes are the variables that we can observe the states of the systems. If you go out and measure something, typically you're measuring something that's in the box. You're measuring bacteria or the combined organic carbon pool, or maybe phytoplankton and zooplankton in the system. The arrows describe how the elements of the system move between the different boxes. And the arrows are generally considered the fluxes in the systems. Sometimes, these terms are thrown around a little bit differently depending upon the environment in which you're modeling. But for now, we'll call the boxes variables or states of the system, and we'll call the arrows fluxes. And carbon, for example, can exist only within the boxes. So when you're trying to plot the time dynamics of the simulation results, what you're really plotting are what's in the boxes. And if you want to check to see whether your simulation is working well, you typically go out and measure things that represent what's in the boxes. And those are the comparisons you're making. There are some exceptions where we do want to try to look directly at the fluxes in the system. Now, interestingly, the way the world works is defined by the combination of the boxes and the arrows. And the arrows really do represent the equations in the system. And we'll look at DOC a little bit more explicitly in the next figure. The magnitude of the arrows matters a lot. And so if we look at DOC here in the middle, it has contributions to its pool, the amount of labeled DOC from the recalcitrant pool of DOC, from zooplankton, from phytoplankton, and from particulate matter that's sitting around. Each of these has either a relatively slow or a relatively high turnover rate. In other words, how quickly does material go from the particulate pool into DOC labile? Well, in this case, it's moderate to slow. Maybe days to weeks is how quickly this turns over. Phytoplankton turn over very quickly, hours to weeks. Zooplankton, somewhat similarly. But the recalcitrant pool of DOC turns over very slowly, months to years. And so if we're observing a change in the DOC pool, which in the real world we tend to combine these, and we're seeing very long, slow dynamics, it's probably due to this recalcitrant pool. If we're seeing very fast dynamics in the system of DOC, high changes from day to day, for example, which are implied by some of the stuff that Dexter, is showing with his figures, it's probably related to things like phytoplankton dynamics in the system, or maybe mixing processes in the system too. It's also important to point out that every one of these boxes has a whole set of arrows, just like the DOC labile does, which is why this becomes really complicated in a hurry once you start modeling a lot of different components to the system. And it's one of the key functions of the software, which is to track, to do the housekeeping for where is, in this case, all the carbon that's in the system. Each one of these components of the overall mass balance equation, is represented by the arrows here. Let's see. So I think we've talked about all of this. All of this, by the way, happens in every single layer of the lake too, which makes it even more complicated and challenging to follow. It's a system of equations, and so we have to keep track of what leaves and what enters between the different pools. This was our labile pool, this is our recalcitrant pool. This points out that whatever we lose from the recalcitrant pool, in this case, goes into the labile pool. This becomes a really handy roadmap, which at first may seem sort of intimidating, but when you want to try to understand what is controlling my observed dissolved organic carbon, these are the only things you have to look at, about half a dozen different things. And trying to track those and figure out where they're coming from and how they're influencing what your predictions are can be really helpful. Now, finally, before we move on to an example of the output, we talk in this project sometimes about, do we have the right equation for how something works in the system? There are two different levels. Do we have the right general equation for DOC that describes the mass balance? And then for each one of these components, for example, mineralization of DOC, does it have the form of equation we're interested in? So in this case, mineralization or respiration, let's say, of DOC is a function of some assumed parameter, just like Robert was changing within the NML files, multiplied by availability of oxygen, which is scaled anywhere from about 0 to 1, depending upon how much oxygen is there, multiplied by temperature correction, which scales this respiration from about 0.2 to about 2. And so whatever we assume for respiration is changed by oxygen and is changed by temperature. And so the question we need to sort of confront is this the right equation? What is the parameterization of this equation? Should we be thinking about this a little bit differently? So that's getting down a little bit into the weeds, but as we look at the trade-off between temperature and oxygen control over organic carbon dynamics in the system, this is kind of where it happens. Right? Okay, and then I think the last slide before we go back into some results, dissolved oxygen is really modeled in 3 different components: atmospheric exchange, which is just the gradient between the atmosphere and the water; sediment oxygen demand, this is kind of a huge one. This is one that's worthy of our group taking a much closer look at, and indeed it's on the agenda. And then there's everything else that happens in the water column, which is a lot. Oxygen is a very fast-moving variable, so it's great for describing biogeochemical processes that are happening at relatively short time scales. That's why it's going to be really important for things like the magic sensor and short-term on-off oxygen experiments that happen within the reservoir. So we don't have a lot of time left. Let me do a real quick check here, Kaylin. Do you want us to wrap up at the top of the hour, or do we have about 10 minutes to talk through an oxygen and carbon set of outputs?
I know that some people needed to leave at noon, so I just wanted to make sure that our folks, the rest of the folks who can stay, are they okay to keep going? If you can still stay, raise your hand. If we can get more than half, I think we're probably good to keep going. Okay. And then for folks who can't join, the plan originally was to take kind of from 12 to 12:30 to wrap up kind of the day, as in this whole morning session, and kind of prep for tomorrow. And so I'm wondering, Paul, if you'd be able to be wrapped up by 12:15, so we'd still have a few minutes to do that.
Oh, easily. Yep. Robert, do you want to show the oxygen example?
Yeah, sure.
Okay.
Oh, sorry. So, okay, so 10, 15 minutes, yeah.
You've got 7 minutes, because I want
got
7 minutes too.
Yeah,
Yep.
sure, I will hurry up. So I'm currently looking at Anoxic dynamics, and just to add to what Paul said about the states, the fluxes, and system scale indicators. So this is like this recent publication by Matt Hipsey and Kaylin also about an assessment of ecosystem, which is really helpful to look at a system. So I'm currently looking at Anoxic dynamics of Lake Mendota. So I'm looking at a variable which is called the anoxic factor, which is used to compare different lakes and how long an anoxia period is in the lake itself. So it will be days per season, for example. And it will calculate actually how much area over how much time is anoxic. So you track down how long and how high, especially high, the anoxia period in the lake is. So here in the script, I just provide a small example on getting that data and how to look at it. So the anoxic factor is really nice just to see or look at how your ecosystem works. So these are some custom-made functions to read in all the data that you have for oxygen at different depth, which also interpolates the data before or while extracting data, you also interpolate the data. You also need a hypsography because you want to see how much area got anoxic, and you have like a critical value. So for this, we say that everything below 1 milligram per liter is anoxic. And then we go through every day and we track down in summer how much or how deep anoxia is and how long. And then we can just plot this and compare this to our data that we had for anoxia, which was calibrated before. So you can see now the first 2 years look okay. We have an anoxic factor of about 65 to 73 days, which probably fits also the observed data. And the next years have a bad fit, so they would predict an anoxic period of only 1 month, a bit more of 1 month. But this is like a good approach to just have like a system scale indicator of how your ecosystem responds. So not looking only at your time series or your contour plots, but also having like a post-processed metric at the end. And to show just how this looks for Lake Mendota, so we run a 4-decade simulation with GLM 82. And at the end, our conclusion was that anoxic area really depends on the heat budget of the system. So here you can see the analysis for 1 year on the left side for 2 heat budgets, which is the Schmidt energy and the Burkean energy. And Schmidt is energy needed to mix the current stratification. So if you have that shouldn't happen. So at the upper right, you can see for Schmidt, currently it's stratified and how much energy would need to get a mixed system. And Burke assumes how much energy you would have needed from an ideally mixed state to the current stratified state. So it's 2 heat budgets about the same thing, but 2 sides of the same metal. And you can see here in this example that once Schmidt and Burke increase in summer, also the anoxic area in Lake Mendota increases suddenly a lot. So there really is a strong relationship between the 2 of them. And then we looked at average values over the course of the 4 decades. So you can see the orange line is the Birchin work, which then increases in summer a lot, and the blue line is the Schmidt stability. So we could identify 2 main periods in Lake Mendota. So the spring mixing event, where the Schmidt is close to 0, so it's ideally mixed. The Birchin work increases a lot, and also the total energy in the whole water column suddenly increased a lot after the spring mixing. And once Schmidt also increases, so we have stratified conditions, the anoxic area of the lake, the red line here, also increases. So at least for Lake Mendota, the lake physics is really driving also the anoxia dynamics. Okay, back to carbon.
Perfect. And just sharing my screen. Okay, can you see this PowerPoint? Yep, okay, good. So I'm not going to run you through the code. I went ahead and previously generated these outputs so we could just jump right into them. But these can be generated very easily with GLM tools by just getting time series data from specific depths and plotting them. And so I have 4 different panels. This is dissolved oxygen at 20 meters, dissolved oxygen at 2, organic carbon speciation at 2 meters and at 20 meters. And let's take a quick look at the annual dynamics, and there's some interesting things to point out for Lake Mendota here. And so first let's go through deep water oxygen. I've highlighted in blue the onset of stratification with a dashed line here vertically to show when the system goes anoxic. So of course in the spring we have stratification. Mendota is highly eutrophic, and so the hypolimnion quickly goes anoxic, stays anoxic until we have mixing again in the fall. And so deep water dissolved oxygen is a great marker for what happens with the rest of the system in terms of biogeochemistry. For dissolved oxygen at the surface, what happens in the deep water doesn't matter too much. The dots, by the way, are observed data. The red line here shows what oxygen would be if it were at saturation with the atmosphere. And the black line is the GLM model. So you can see that GLM is consistently over predicting the saturation level of oxygen. We have too much oxygen in the system compared to what we observe. Why is that? Well, let's go down to the organic carbon panel here. So this shows speciation of organic carbon, both dissolved fractions and particulate. The total dissolved fraction is the black line. The recalcitrant organic carbon is the green line. So you can see the long-term mean, and in fact the long-term decrease in organic carbon is really driven by the recalcitrant fraction of the system. Any short-term changes that we see are due to primary production that are in the system. We're not matching the observed short-term changes in organic carbon very well. So probably we need to transfer what's happening in primary production into that organic carbon pool a little bit more effectively. This dashed line shows the phytoplankton and their dynamics in the system, and you see we do get a little bit of an organic matter bump from the phytoplankton each summer, but it's not enough to kind of bring us up to where we need to be. If we go down into the deep water for organic carbon, we do see, again, the long-term trend driven by the recalcitrant fraction. It's a very slow turnover pool, so it can't affect the short-term dynamics of the system. But we do see this bump, and that bump occurs about the time we go anoxic. So that bump in dissolved organic carbon deep in the lake is due to the onset of anoxia in the system. Now I want to show you in just the next few minutes remaining. I'm going to skip over phosphorus and sort of a combined phosphorus organic carbon slide and go straight to an experiment where what we are trying to do is switch phytoplankton output into particulate organic matter. We have this problem of when we have a lot of primary production on the surface, we're also building up too much oxygen in the surface. And so we need to accommodate for that. And so we have our base scenario, which is what I just showed you, which we have too much dissolved oxygen in the surface. We're not getting much of a bump in organic carbon, and we have low dissolved and particulate fractions. If we just go in and we change the output of the phytoplankton to more particulate matter and make that particulate organic carbon decay more slowly, we see a nice big bump in organic matter that's happening near the surface.
Paul, can I interrupt super briefly for just a second, because we're about to lose a bunch of people that have to log off, and they wanted to make some announcements for tomorrow first. Quinn, do you want to go really quickly about the software updates for the tutorial?
Oh yeah, so, sorry, Paul. I have to. I have to go do childcare. So I just wanted to. I think Bethany will email out a link. So I believe that everyone probably will be able to access the Flare code tomorrow. The way I recommend doing it is by installing Docker Hub on your computer, or Docker Desktop on your computer. And there'll be instructions sent out about doing that. And if you can do that, as long as you don't have Windows Home Edition, that if you have anything other than Windows Home Edition, you have a Mac or a Unix computer, you'll be able to run Flare in a container. And so if you can get there, then you'll also get more out of the container discussion that Renato will have, the training that Renato will do on containers.
And Bethany, you'll be sending out that link if that's okay. Great.
Yeah, it's actually, and you can look at the user's guide that is now in the chat here. I'm not going to be giving a presentation tomorrow. We'll be working through the user's guide is the presentation. So yeah, Ryan tested the Docker container on Windows, so it worked. He has Pro. I don't know when people get home, but
I think it's supposed to be working on Home Edition now too,
okay.
Quinn. Yeah, but if somebody has it and can give it a try, that'd be good to know.
Great.
Awesome. Thanks. And Renato, in terms of software for tomorrow, is there anything else on your side?
I mean, if people try to install the Docker desktop with instructions in the user guide, that's great. But I'm going to do the demo without trying to get everybody to do it at the same time, because I think that would be too complex. So it's something you can try before the meeting, during the meeting, or after the meeting. But I'm gonna do the demo from my computer. So.
Yeah. So the Docker desktop is for running Flare later on, and it's 1C. That'll be the email that gets sent out. There's three different. The user's guide talks about 3 different ways to get Flare on your computer, ranging from downloading the Dropbox set of folders to fully getting your computer up and going with real-time access to the files or for the data from FCR, to using a Docker container. And the Docker container is the most likely to work on your computer because that's what Docker does. And Renato did an awesome job putting together a Docker container that we've tested across multiple machines.
Awesome. Sorry, Paul, to interrupt. If you want to go back to your example.
Oh, no problem. No problem at all. I think we're basically done, because we can kind of dive into those figures in a lot of detail, and they're fairly complicated. But the main point I was trying to make with those figures is that if you kind of go back to your ecological training and your understanding of biogeochemistry, and you can sort of ask the question of, how should material move through the system? What do I really expect in terms of dominant biogeochemical process or biological process at particular time and space scales. There are ways to go in and specifically test those ideas and connect those ideas with the predictions that are being made. And in some ways, I think that's where kind of the talent of calibration comes in. Moving organic carbon from the surface down to the bottom so that it maps better onto how you think the world works, as one example, is something that's really, really challenging to do in an automated calibration environment. So instead, relying on your expertise, I think is sometimes more fruitful, and trying to marry your expertise with your understanding of how the software works is why it takes a while. But we're here to help. Finally, I just want to thank Robert again. Robert, I know you put a lot of time into this. Your expertise shines through amazingly well. Having somebody on our broader team who understands the physics, the software, and the biogeochemistry is incredibly helpful. So thank you, and thanks to everybody for showing up today. It was fun.
One more thing before we stop. I just want to say, if you want to one example again, just add simso feedback to false in small letters. Yeah, then it works. If you have capital letters, it won't work. Small letters is the way to go. Yeah, thank you, Mary, for pointing this out.
Yep, details.
But then the script should work. So yeah, thank you all.
Thank you.